Hi, this is a presentation of the paper Articulation GAN, Unsupervised Modeling of Articulatory Learning from Gašper Beguš, Alan Zhou, Peter Wu, and Gopala Anumanchipalli. So, most unsupervised speech synthesis models are trained to directly generate waveforms or spectral data, but humans usually produce speech by performing articulatory gestures. So when we speak, we usually don't spontaneously produce a full waveform or a full spectral GAN. We usually speak by moving our articulators, so our mouth, our tongue, our lips. So our question is whether or not an unsupervised speech synthesis model can do the same thing, whether or not a model like this can learn to produce speech using human-like articulatory gestures. So we begin by proposing an unsupervised setup in which a deep generative model must learn to produce articulatory gestures in order to actually produce intelligible speech. We'll show that the articulatory gestures produced by the model resemble human gestures both qualitatively and quantitatively. We'll show that compared to a baseline, the articulatory model produces speech outputs that are slightly less intelligible, but much more innovative. And finally, we'll argue that this model represents a much more cognitively plausible model of how humans learn to produce speech. So jumping right into our model, our articulation GAN is comprised of these sort of three subnetworks. And the sort of key network here is the physical model here in blue in the middle. And what this model does is it takes as input these 12 channels of EMA plus voicing, and maps them onto some corresponding speech output. So EMA, or electromagnetic articulography, is a method of measuring articulation in humans, and we choose this as our sort of articulatory representation for our model. And in our case, we have the X and Y coordinates of each of these individual articulators, so the lower incisor, the lower lip, the tongue body, etc., as well as this additional channel of voicing that you can't get from just the lip or the tongue. And so given the sort of trajectories for each of these articulators was voicing, this physical model must map this on to the speech output that these gestures would have produced in a real human. The rest of the model, the articulatory generator and the discriminator, are more what you would expect to see in a GAN format. So the generator takes its input, some latent noise Z, and it maps it onto some output G of Z. But here G of Z is not the direct speech waveform itself, but actually this 12-channel EMA plus voicing representation that we just talked about before, which then gets passed through the physical model to be turned into speech. The discriminator takes its input real speech data, which we get from Timid, or generated speech data that follows this entire process from noise to EMA to speech, and it needs to assign a realness score to its input. And as per usual in the GAN setup, the generator and discriminator are trained in this sort of zero-sum game, and hopefully at equilibrium, the articulatory generator is producing representations whose speech mapping is near indistinguishable from the training data speech. And hopefully this also means that it has learned to produce channels of EMA that are similar to what humans have done. So to actually train our model, we actually trained this physical model here in the middle separately to map between EMA and speech. And this is done on this MNGU0 data set, which consists of EMA data and speech outputs from one male British speaker of English. After this model is trained, we actually freeze it before we train the rest of the model on speech outputs alone. So first we train this on the EMA to speech task, and then we freeze the weights here and train the generator and discriminator like we do in a normal GAN setup on just speech outputs from Timid. In this case, we chose 8 words from Timid, which is a corpus sampled from a variety of speakers of American English. And then finally, we train a wave GAN model whose architecture is very similar to our articulation GAN model. Just instead of having this physical model, the output of the articulatory generator is just the speech itself. And we train this on the exact same words from Timid as our articulation GAN. So looking at the performance of our model, we start by looking at the actual speech outputs of articulation GAN and wave GAN. And so we hired a trained phonetician to transcribe the speech outputs of both models and to annotate them as either intelligible or unintelligible, where intelligible just means that they are able to transcribe the speech, and unintelligible means that they are not able to transcribe the speech. And we further annotate the intelligible outputs as innovative if they did not appear in the training data. So here you can see that while wave GAN is a little bit more intelligible than articulation GAN, with 87% of its outputs being marked as intelligible compared to 72%. It's a lot less innovative than articulation GAN, with only 50% of its intelligible outputs being annotated as innovative compared to 77% from articulation GAN. To actually analyze the articulatory representations themselves, we actually have to do a little bit of data cleanup. So we don't impose any restrictions on the articulatory generator. So sometimes it produces these very extremely fast movements. You can see these like jagged movements in black, which are much faster than what a human can do with their articulators. And to counteract this, we just smooth the raw rapid movements using lowest smoothing. And so we have an example here of this here, where we see the raw outputs from the generator in black with these very fast rapid movements. And in blue, we see the actual trajectory of the articulator after smoothing. After we do this sort of smoothing cleanup, we can basically just compare the representations one-on-one with real EMA data. So here we're just qualitatively comparing the real and generated EMA data. On the left here, we have the EMA channels in blue, the real EMA channels in blue rather, and the smooth generated EMA channels in green for the word wash on the left here and the word fast on the right here. And we see broadly that like these gestures are very similar, especially for wash, the lower incisor, the lower lip, the thumb body all have these very similar sort of trajectory. The trajectory is a little bit less similar for fast for things like the thumb body, but we still see the sort of same general idea in places like the tongue tip or the lower lip. And so to sort of quantify this comparison a little bit more, we actually do dynamic time warping of the time series of the two time series for the real and generated EMA, and we take the Pearson's product moment correlation for both of them. And now quantitatively, we can see that there are very high similarities for the real and generated EMA. So for wash, we see very high correlations for everything except for X on the lower lip. And then especially for the y-axis of each channel, we see extremely high correlations between real and generated EMA for wash. For fast, we see almost identical correlations for tongue tip and lower lip, and just very broadly high correlations elsewhere. And so from this, we conclude that the articulatory generator is learning to produce gestures that are similar to human articulation. Yeah, so just to conclude, our model is able to generate human-like articulatory gestures in a fully unsupervised setting. But while our model is somewhat less intelligible than a traditional model, it also produces a much higher proportion of innovative, intelligible outputs. And finally, we argue that this model is not only a more cognitively plausible model of how humans learn to produce speech, not by generating an entire waveform, but by learning to produce with articulators. But it's also potentially useful for creating more realistic speech synthesis technologies using articulation as a prior. And with that, I'll thank you for your time, and feel free to reach out to any of us by email or through the Berkeley Speech and Computation Lab Twitter. Thank you.